Hello. Hello. Do you hear me or not? Please type in the chat. Hello, do you hear me? Okay, thank you. Sorry, I have some trouble. This is my first stream, so I a little nervous, and I see that something goes wrong. So sorry for that delay, and my name Andrei Mohamed, and I'm protection control engineer and NPC Ukrenergo, and I'm past 2 years I investigated more than 400 events, and wrote more than 9 detailed reports about them. So I look at fault records mostly every day, and for me the control files viewers are very important, and now in the market we have two great programs, one from Synchro and other from Siemens, Sigra, and I like them a lot, but I have some issues with them. Firstly, because I have a hybrid workflow, and my company can afford licenses for office computers, but I can have these programs at my home computer. So what's more, this software is more like the companies build their own ecosystem for their product, and they don't want to customers to leave this ecosystem, but we all have a lot of vendors, and I want to have features that allows me analyze IDs from every vendor. And my company has many digital fault records, and usually the record from such device has 32 analog channels, and if you try to open this file in Synchro, you can't see whole picture of the event, and you need to make a lot of moves to see values, RMS value or values or instantaneous values, and also in Siemens to see these values you need also make some moves, and Siemens has great features that allows you to analyze distance protection, build distance characteristics, calculate impedances, and I want to have such features for all vendors. I want to analyze ABB like that, or GE. So all these are the reasons why I developing my own app, and it's web-based, so I can see contract files at home or in the office, and I use this software a lot, and today I show how I usually use this software to analyze events. And I have plans. I believe that I can divide them on like more technical plans and a little bit more vision of what I want to achieve by this app. And from technical point of view, the next things that I'll add will be fault location. I want to allow user to make its own database, to have a statistic. Because when I'm working and sometimes I have similar cases, so I want to quickly find in my database files the same files, and I want to have access to my cloud. So the next things that will be added to the app is are these abilities to work with big quantity of files. And what my like bigger view, bigger vision. You know, I'm some time ago I wrote a post about IEC 61 and 50 because now I have a challenge to learn it, and there is a lack of information how how to implement solutions. So I want to make place where people can communicate, where they can study, help each other, and one of these things I want to make monthly case studies, and this one is the first one. So it's like my experiment, and I want to find the way how I can make them, but and make them not so boring, no. But I understand that such video is not entertainment videos, but you know, I want that make interesting videos. So I'm planning to shoot course about fault investigation. So let's switch to the case study. Please, if you have questions, write it in the chat. When I need to pause, I'll go through the chat and answer these questions. So in the beginning we go through the primary scheme. This is a very simplified scheme. We have a wind farm, 75 megawatts with type 4 wind turbines. Usually it's connected to the grid by two lines, but in this case only power flow can be go to the grid only through the one line. So and one moment that on this substation C there are a lot of load. So we have three substations, 110 kilovolt A, B, C, and this primary scheme. Let's dive in a little bit to the this line. So and I want to talk a little bit about relay protection philosophy. So on that line installed two main protections, RED 670 from Hitachi Energy, and there are not only differential protection but also backup protection, like distance protection and ground over current protection. Also there are some features like from the that historically was happened in such lines. No, in Soviet Union usually for single phase fault are used ground over current protection. Usually there are 4 stages, and for multi-phase faults were used distance protection. So in this case we have the same. So RED have phase differential protection, ground over current protection, and distance protection. Also we have usually transmit through the communication channel commands, like it's not like direct transfer trip, but usually in this type of communication we transmit three commands. So first command is with R inhibition, second command with only trip with following R, and third command is like POTT scheme, but it's a little bit different because the third zone of distance protection and third zone of over current protection are used for this scheme. Also in Ukraine most trips followed by R, except next functions: breaker failure protection, the SOTF functions, and also system integrity schemes trip from these protections with R inhibition. So okay, and usually the pause in our cycle is about from 2 to 4 seconds. In this case, on substation A, the R pause was about 2 seconds, and on the substation B, R was about 2.5 seconds. In such case, the communication channel was damaged, so differential protection was not in service. When I show you records, you will see that that channel was restored, but it was not verified by protection staff. So in this case, on line protected only by backup functions in these IDs. What I believe that please, do you have any questions? Okay, let's go to the a little bit how in Ukraine about requirements in Ukraine to the wind turbines. So I believe that in most countries there are a lot of codes, and Ukraine also have such type of codes that prescribe behavior of the wind farm or solar farm through to their response to the short circuit. And I believe that you may see such pictures. So what areas we can see? So in area A, on the top, the wind farm should always be connected to the grid. In area B, in this area, wind farm also has to be connected to the grid, but it must begin to produce reactive power, and this production must start from the time at least 100 milliseconds, and I show you this thing. And in area C, wind farm should be disconnected from the grid. What more, in area B, the wind farm should not decrease their power production. So if to return to short circuit, we have short circuit here, and it was something around 1 kilometer from the substation B. I want to show you record from the low side. This record is not from this particular event, because we don't ask to records with this case, but you can see the behavior. So on the top there are 3 currents, 0 sequence current, 0 sequence voltages. So to show the power flow, firstly I add power channels. We have calculation for 3 power and single phase power. So I select 3 power. Units from voltage units kilovolts, so I have to choose kilovolts. I'm selecting channels for calculation and also currents, all kind of power. Sorry. Okay. I've not clicked to calculate apparent power. One moment. I repeat. minutes to. Okay, so let's you can see that from this moment wind farm not started to produce reactive power, but because we see positive values, what you can see instantaneous values 1.8 megawatt with a positive value, so it's receiving power. But later, after 160 milliseconds, it starts to produce reactive power. So this time was spent by inverter to begin to switch in different mode and begin to produce reactive power. And also we can on the top we can see apparent power, and in this case RMS instantaneous value 9.9 MVA, and during event it changed around this value. So in this area where reactive power started to produce, we can see 10 MVA and so on. So in this case the wind turbine was tripped by over voltage protection, but in today's case study and the behavior was a little bit different, and I describe it a little bit later. So let's move and look to the short circuit from substation A. Okay, what we can see, as I told you, this is channels from the remote side, and I repeat that in this particular case the communication channel was restored but not in service. So we see moment. I see that not all channels are viewed. We can see that fault started with phase B, then phase B, C, and at this point the current stopped to flow on the phase A, but the voltage drop is not too big on the phase A. So let's look from the to the opposite side, substation B. So here you can see a little bit different picture, because in the beginning we see that there are two-phase short circuit, and also big enough current on phase A. So on phase C is 1386, and for on phase A around 700, on phase B around 800, and we can see pause and something spike, strange spike after R, and then very little current and almost zero voltage. So it's difficult to understand and see what happened, and that's why I want to unite two files from substation B, because this is the ending of the event, and first I want to unite them and then add to the substation A, so we can see what happened during the events, looking on the both sides. I want the serial connection, and a little bit more time. Okay, we can see now the whole events. Now I want to add here a record from substation A. So you can see that the records and IDs was not synchronized, so I have to do it by hand. With green background color, record from the different ID, so this is how I can differ from one from other. So on the bottom we will have a record from substation A. On the top we have a record from substation B, and I hide all unnecessary channels to that we don't have so messy workflow. Okay, so I need to put the red cursor is responsible from the for top record, and the black is responsible for the bottom. So okay, it seems like that didn't match, but I check one more time. I put cursors on the beginning of the event, so okay, we have a little 16-second difference, and I one more time synchronize. Okay, so if this is the analog channel for the neutral current, and we can see that there was some current in neutral, and if we look to in the FAC, we can see that the current value is almost zero. So and at this point there was some current, and after that point of time the current is zero, but appears a neutral current. So we make suggestions that before short circuit there was open pole on broken conductor, and if we return to the primary scheme, so on the left, like substation A, A and on the right is substation B. So we can see something like that before the short circuit. Okay, now I want to build vector diagrams from in the beginning from the substation A. So this knob with B is a knob to make any channel like a base channel. So I want to make phase B voltage as base channel and add currents to the first vector diagrams. Okay, we in the beginning of that record we also can see that something strange is happening, and during fault in this case we see like a three-phase short circuit, but actually this is the voltage decreased in only in two phase. Phase A voltage is almost healthy. Let's look at the substation B. Almost every strange look. Sorry, something strange. Somehow, sorry. I don't understand, something goes wrong. Sorry. Okay. You know, but what you already can see that very strange vector diagrams, and it's difficult to understand what's happening at this moment. So on the top, I want to remind firstly for myself that on the top we have a record from substation B. This is like this substation. So let's return to this picture. So before the short circuit we have broken conductor on phase C, and that's why we don't see short circuit at the first time from the on the record from the substation B. So when short circuit occurs, we see only phase B and phase A. But if in phase B the current was around 2 kiloamperes, in phase A it was something around 800 amperes, and we also don't see decrease in voltage A. At this point, it's 67 kilovolts, from to the 110 grid, it's normal voltage, phase voltage. So if we return to this picture, we have something like that. And because we have zero sequence current, we have short circuit to the ground. So in the first study of the short circuit, we see that picture. So from the substation A perspective, we see only phase B to ground short circuit, but from the substation B, we see the two-phase increasing current in two phase. So and this corresponding to like this type of fault. Okay, but then we see that current in phase C increased. I want to remind firstly for myself that on the top with this green background we can see the record from the substation A. So this means that from this point there was also two phase short circuit, and here from substation B perspective we also see the currents in phase B and C, and I want to put your attention that voltage is a little bit lower, but it also 65 kilovolts, so it's like healthy phase. So what does it mean? So it means that we see something like that at this point, and here we can see the trip from the substation B side. That's why from substation A in this moment we see that a current became almost zero, 2 amperes primary. So let's return to this picture. So and now from substation A we see like two-phase short circuit. And I want to add remove phase A, but you can see that the angle between phase A and C is almost 120 degrees, and the current in neutral, this purple channel, is like turned to 180 degrees current from AC. So it's very strange look, like if we turn the neutral current to 180 degrees, we will see the phase A current. And let's look on numbers. On phase B we have almost 6 kiloamperes. On phase C almost 5 kiloamperes, and in neutral is almost 4 kiloamperes. But at this point I want to remind for myself that we can see a decrease in the voltage on the phase B and C. So let's return to this point and look at the this is vector diagram from the current vector diagram from the substation A. So we look at substation B, and this is very very strange look, because it's easier to think that power flow something like that through this short circuit. But if to look on the vector diagrams, we will see that currents is almost have the same direction, and this is very interesting case for me, and I have only one explanation to that, and we to explain it, I need to build a little bit deeper vector diagram. So let's check the power direction from each phase. So I add to the vector diagram voltage and current, and you can see at this point that we have like a capacitive character of the current, but it's difficult to say is the power is received by substation through the line, or it the power flows from the substation side. So let's see what's happening in phase B. Okay. This vector diagram shows that on phase B the power flow also from the substation, not to substation. And let's see substation phase C, the same picture. So the real picture of the power flow that we see is something like that. And from the substation A perspective, it will be something like that. Very strange picture. It's not usually what we have to see in short circuit, but I started in the beginning that short circuit was around 1 kilometer from this substation. Let's switch on and what explanation I have. So one moment. we usually simplify the picture, but we have to remember that we have like arc resistance, and in this particular case looks like this arc impedance was bigger than impedance of the this little part of line, and also impedance, zero sequence impedance on the transformers, because here we have two 40 megawatt transformers with grounded neutral, and they work in parallel. So it looks like in this case these impedances was smaller than this arc impedance, so the current flows in this strange manner. So please, if you have any other ideas, please write them in the comments or ask questions, and I'll be happy to see other opinion. But at this point I have only this explanation, and so from substation A point of view we can almost see like three-phase short circuit. And if we look to the vector diagram at this point, this is substation A. Let's look. So the degrees between phase currents is almost like we see the three-phase short circuit. And for me it's because these impedances are so low that we can see this whole scheme like one point, and in that point there will be that direction of the power flow. So let's move to a later moment. So the short circuit from substation A was tripped a little bit longer, but if we measure time here, our R pause and unsuccessful R from substation A, and at this point we can see that there is only phase C to ground short circuit. And what this transient, what happened? So the reason is that at this moment this is our pause for substation B. The circuit breaker was switched on. So explanation of this transient, let's look to the voltages. So let's return to the primary scheme. So I draw these VT transformers to show you where it's located. So after line was disconnected, we see something like that. So usually when designers designed and settings engineers made studies. They think that when wind farm disconnected from the grid, it just stopped to generate. But in this case, it not happened. So because of this load, there was island from with wind farm and load. So let's return to that's why we see voltages on these voltage transformers, and also these are voltages from substation A. Here. And let's look to a little bit. Okay, so let's find zero crossing voltage A, phase A voltage, and now you can see that it's not synchronized. So difference in time between them is like about 6 milliseconds, and we can see in degrees, so it's like 118 degrees between them. Let's switch to the milliseconds. So that's why we see this current transient, because the circuit breaker from substation B side switched non-synchronous to the grid. So the first circuit breaker closed from the substation A, and then it was closed from the substation B. And because of this difference in phasors of the voltages, we can see this transient. But why it's so short? That's what because at this moment substation B was tripped by the SOT function, and we see this picture, like the wind farm is switched on the short circuit. Here and because of the very low zero sequence current, we see so long tripping time. So as I said in the beginning, we in Ukraine we have usually for SOTF functions we use third zone of the distance protection, and also third zone of the neutral ground over current protection. And in this particular case, the third zone was 800 amperes, and at this moment the ground current was a little bit more than 300 amperes. So this SOTF function can't work in this particular case. And why we have such time? This is like 1.5 seconds. So let's return to this picture. And this is like a border of with 1.5 seconds when after that time wind farm has have to be switched off from the grid. So that's why it was disconnected, and usually it disconnected by under voltage protection functions, or in this particular case under voltage. But if you remember, I showed you this record. In this case, the wind turbine was tripped by over voltage protection. But if to return to this particular case, this 1.5 seconds is because of that picture. So we can say that wind farm was behave like it required from our code. So let's guys, I want to do you have any questions? Please, if you have it, I book. Okay, I look a little bit later. So let's look on the protection behavior. Now, at this point, we analyzed on the like analog channel behavior. What happened with primary equipment, but let's a little bit dive in protection itself. So here we have trip, and it was by the zero sequence over current protection. Let's check timings. But almost half of the second. The main thing I want to check at this point is this is substation A. We can see that at this point there is almost seen like three-phase short circuit. So if we have different protection, why first or second zone just don't trip? So I want to check the distance protections from the substation A side. So let's go to the relay protection. I just add two zones, check face-to-face loop, and insert settings only for multi-phase short circuits. And second zone. So this is how our different zones looks like. Let's add impedance calculator and link analog channels to that impedance calculator. So this is our phase A current, phase B, phase C, voltages. Okay. And we can see that first zone can't operate And if we return to this picture, I've already said you that this short circuit was something around 1 kilometer from substation B, with overall line was something around 13 kilometers. So that's why second zone should operate. But the second zone time was a bit long, about 0.8 seconds. So we just don't have time. And if we look at the impedance behavior, we see that only at this point impedance went to the second zone, and it was near the third zone, but unfortunately it was not in third zone. So let's check what happened in substation B with so check links, because files are pretty much the same, so I don't need to relink them. I only need to check zone settings. So my first zone to bit differ is and you see the impedances, and this one more proof that we see such power flow in primary scheme. So what more interesting was in this particular case? Here we have a trip, 20 milliseconds, but look at this digital channel that's called EF second harm. In this particular relay, the second harmonic blocking was enabled on neutral overcurrent protection, and that was lead of the lead fault. This happened because of here we can see the 0 sequence current. This like little movement of the phasor, and the relay is see that like second harmonic, and you can see here that it was something around 23%, and but the setting it was for that blocking was low enough, something around 20%. So because of this we almost doubled the time of the tripping. So I believe I describe all I want, and the final thing that I want to add is like things that I learned from this particular case. So the first thing is nobody expected that wind farm will produce electricity power while it will be disconnected from the grid. And I really don't know how to fix that or implement some solution, because everyone expected that in this case wind farm should just stop generating, but it's not, and this was and because of this we can see the non-synchronous connection this to the grid, like this wind farm to grid. Sorry for a mess. What more? Because I'm working on a team, and I see some problems, sometimes I can fix, and in this particular case I can't fix that second harmonic blocking, because in my company I just investigate faults, I don't calculate settings, and I describe this case to the setting calculation engineers, but it's their decision to change or not something. What more? I don't like that our settings engineers don't use distance protection for single phase faults, and I believe that in this case we may have more faster clearing time. What another lesson learned, that after IR the zero sequence current was not enough to activate SOTF TF function. So we also, if you want to tune a protection to optimal operation, we need to change SOTF function from third zone of neutral overcurrent to fourth zone. And one last moment that I learned, that in the beginning I said about codes in my country, but unfortunately these codes not require or prescribe who is responsible for checking of the wind farm behavior and procedure of what we should do if something is differ from what prescribed in these codes. So for me it doesn't matter how behave the wind farm behave, especially I don't understand or for me it's strange why it need to produce reactive power. So for me it's like more dispatching issue, you know, because when we have short circuit and wind farm produce reactive power, the voltage levels are higher. So this means that impedances that measured by distance protections is more than it should be if there was no wind farm. And this is a little bit challenging for setting protection, setting calculation engineers. And I want, you know, Ukraine is connected to the INSOE grid, and on the INSOE website there are a lot of documents, and I want to recommend this document that are called Short Circuit Contribution of New Generating Units. And here's some very interesting pictures, and how different types of wind farms works, wind turbines works, and how their contribution impacts on the protections. So at this moment it's all. Now I check, maybe you have questions. Так, I see. Remote sub-distance relay in service, show how blocking. I don't understand this question. Let's return to the this picture. So in this case, we only don't have had communication channel between these two protections. So and from each side there its own backup protection functions on the RD 670s with their own distance and ground over current protections. I don't know if I asked these questions. So and when this communication channel in work, we don't use blocking scheme. We use permissive like POTT schemes, not blocking schemes. The bus A is strong and bus B is weak, and secondary side of the transformer at B probably delta. Because of that, you can see that current same magnitude and same angle and the current waveform. Yes, this substation A is very strong. I show you very simplified part of the grid, and there are more than 110 kilovolt lines for 330 kilovolt lines. So yes, this substation A is a powerful transmission substation. If power flow direction changes, show that on impedance plane. I believe I already showed this. In what software you did this simulation? This is not the simulation. This is a real life case, so I don't need to simulate anything. The life is better than any simulations. I have to check all the details, but this is my first. Okay, guys, thank you for your time and interest. I hope that it not was so boring or too boring for you, and see you next time. Please, if you have any questions or you can provide any feedback, type it in the comment. I'll appreciate it. Okay, thank you very much. See you next time.